Hello everyone, I'm Jesse Mason, and in this edition of Teach Me, we're going to determine the impact speed of a dropped object using kinematics. So first we start by drawing a picture. When problem solving, you always want to start with visualization. So here's a picture of a person dropping an object of mass m from a tall structure. It looks like maybe a water tower, 50 meters tall. And before any of you architectural naysayers question the legitimacy of my drawing, I just want to point out that structures like this water tower here do exist. This is a picture of the Ypsilanti water tower, in front of which I proposed to my wife. I know, I'm a hopeless romantic. So what is the impact speed of our dropped object? It would seem that we don't have enough information to solve this problem. The only thing we're given is the initial vertical displacement, but there's a couple pieces of implied information, like the initial velocity. We said it was dropped. That means the initial velocity is 0. Oh, and we should probably indicate the impact on the drawing as well. So I'm going to put that down here along with a little note that we're looking for the velocity. So we're given the initial velocity by implication. We're also given the acceleration of this object by implication. We said that the object was dropped, and that means the object is in free fall. And an object in free fall acts solely under the influence of gravity and accelerates toward the ground at a rate of 9.8 meters per second. By the way, this number is so important we give it its own constant, g, for gravitational acceleration. So I'm going to indicate that acceleration right here. And now we have enough information to solve our problem. We just need to select the right equation to do so. There are 3 equations that we can use to analyze a body undergoing constant acceleration. They are called the kinematic equations. Some of us in Detroit affectionately refer to them as the big 3. The first of which is the velocity equation. Here t represents time. And if we integrate the velocity equation with respect to time, we get the displacement equation. Here s represents displacement. And if we combine these 2 equations, we can get a third equation without t as a variable, and we call that the time-independent equation. These equations are so important to beginning physics students that you should memorize them, or at least have them written down somewhere where you can access them, because you can analyze any situation that involves constant acceleration with just these 3 tools. So I'm going to box these equations up in red, which in my notes always means very important equations! So, of these 3 equations, the most appropriate for our problem is going to be the time-independent equation, because we lack any information about time. So I'm going to rewrite this for the y direction. So we have vy squared is equal to v0y squared plus 2ay times y minus y0. Next, I'm going to look for some terms that I can set to 0, simplify things a bit. Since our object was dropped and its initial velocity is 0, we can set this term to 0. I also know that the final vertical displacement of this box, y, is going to be 0 because it strikes the ground. So I set this to 0. And for simplicity's sake, I'm going to set ay to g. Okay, now that we have some of the terms out of the way, we're going to rewrite our equation. Vy is equal to 2 times g times negative y0. Don't forget that negative sign. And since vy was squared, we're going to take the square root of this side of the equation. And we're done. We just have to plug in our initial values. So vy is equal to the square root of 2 times 9.8 meters per second squared times negative 50 meters. Wait a minute. Wait just a minute. I see a negative product under that square root sign, and that makes me really uncomfortable. It should make you uncomfortable too. Until you realize the acceleration of our object is downward. And we defined upwards as the positive y direction, albeit somewhat informally. So let's write our coordinate system here with positive y in the upward direction. Just for funsies, positive x in the right direction. So this tells us that that value for acceleration is negative, which makes that product under the square root sign positive. Whew! Averted disaster. So we have Vy is equal to 31.3 meters per second. So there we have it, using kinematic equations to determine the impact speed of a dropped object. I'm Jesse Mason, and I hope you found this helpful. And until next time, happy learning.